So we've covered already several reactions, and as you guys uh, remember and realize, these reactions are pretty big chunks of information. But if you know how to recognize the important functional groups that are involved in the reaction mechanism, then you should be able to put together a reasonable reaction mechanism. Okay. Now, the next set of reactions are Michael addition reaction coming first. And let's take a look at the components that will be present in this reaction. In the role of your nucleophile, you can use whatever nucleophile you want, okay? It can be just a simple nucleophile such as methoxide under right conditions. It could be Grignard reagent. It could be organometallic lithium, or it could be the enolate. Okay, but since we're covering the chapter with enolates, let's do the example with enolates first, and then we will present a couple of other possibilities. So your nucleophile, just for the sake of this chapter, let's choose a good enolate here. So we have an alpha position with available protons. And for the electrophile, we're going to use an enon. Now, what is enon? Enons are the compounds in which we have both double bond from carbon to carbon conjugated with the carbonyl. Okay, so in stands for the double bond, and on stands for the ketone. The reaction is done under basic conditions. And let's see what will be the outcome of this reaction. Well, hopefully we're already comfortable with your carbonyl compound becoming a good nucleophile under basic conditions. We abstract alpha proton, we form an enol, and then it will bounce back to form a good nucleophile. Let's take a look at the properties of enon and recognize what will be the electrophilic center in the enon. Well, the first impression would be that once we put a negative charge on this carbon, it will attack the carbonyl carbon because it's right next to the oxygen, so it should have the least amount of electron density on it. However, that's not true. Our hypothesis and the actual experimental outcomes do work together very comfortably. So if we look at the structure of enon, we can have resonance from carbon to carbon double bond all the way to the carbonyl oxygen. And the result of such resonance is going to give us a structure in which we'll have negative charge residing on oxygen, and then we will have formal positive charge for incomplete octet on the carbon. So your carbonyl never becomes an incomplete octet, while the carbon on the double bond is, and that will make it into your electrophilic carbon. Okay, so this is going to be your electrophilic position. And this is going to be your nucleophilic position. Okay. So let's take a look at the mechanism of the reaction. Again, understand the patterns, understand the expected features on the product and the starting materials, and then we will run the examples. We're going to choose to use just the examples that I showed above. Guys, I see that very many of you in mechanisms do ignore the resonance, and you lose a lot of points for that. If the resonance is there, it shows the stabilization of the intermediates, and you have to respect that. So let's choose a base. Obstruct that alpha proton, form a double bond, move the electrons onto the carbon. Also, the arrows should be meaningful. Sometimes on the exam, you will just put arrows just anywhere. And if they're meaningless, then they are not deserving any point recognition. So let's see, we are forming methanol as a byproduct. We need to acknowledge that. And the double bond is formed here. So it's an enolate now. And then it's going to bounce back the electron density and react with your enone. So when the electron density comes back, we're going to attack this electrophilic carbon. Electrons will move onto carbonyl oxygen, and the intermediate here will look like this. I'm going to put the newly formed bond in different colors so it will be well visible. And then now we will put the rest of the molecule here. Let's identify that electrophilic carbon and nucleophilic carbon so it's well visible for you guys. And then we have a double bond here, and the electron density moved onto the oxygen. Well, this is not a very good resonance delocalized structure. Of course, we get a negative charge here now, moving from oxygen of the nucleophile on the oxygen of the electrophilic portion of the molecule. Electron density is going to bounce back and all the way on the carbon adjacent to your beta carbon. Let me put in the identifiers here so you will be able to follow it very well. Alpha carbon, now it's a beta carbon in the product, and this is a gamma carbon on the next position. So that's the carbons that will acquire a negative charge as a result of this resonance delocalization. Okay, and let me identify again all the carbons so you will have a good feedback later on when you review this. So now we have a negative charge on this position, and we can easily protonate that position. We just produce methanol, and methanol is a solvent of the reaction. If it were water, you would be using water. Obstruct the proton, form methoxide. And our product is ready to use. Okay, so now that we did put the product together, let's compare it with the starting materials, and let's see what is the good way of recognizing the product of the reaction as a product of Michael's addition. Okay, we're going to highlight the starting materials as our nucleophile. And here we are. And the electrophile and once we do that, we can see the differences. While visibly, nothing is changed on nucleophilic portion of the molecule, we formed a new bond indeed. And this is from the alpha carbon next to the carbonyl. We can recognize that part as the nucleophilic portion of the molecule with given reagents. Then on electrophilic portion of the molecule, we can see that the double bond here is gone in the product. Carbonyl is there. So you had one double bond and it is gone because of that resonance delocalization of electron density and then protonation of the carbon. Okay? How would you see it as a Michael addition product? The way to recognize it, you would say, well, it's diketone. We did talk about diketones already, but those were 1,3 diketones. In Michael addition product, it's definitely not going to be a 1,3 diketone. The distance between two carbonyls will be larger. Okay? And if the starting materials are given, or at least one of the starting materials was given, then you can definitely recognize and predict the structure of the other one. Any questions here before we move on to one more example? If there are none, let's move on to the next example. Let's make up something here. So let's take a look at this example. So in this case, we're given the reaction conditions. We have two carbonyl compounds. One of them is enone, the other one is just a ketone. We recognize that the ketone will be playing the role of the nucleophile. Now, in the presence of a larger base, out of two available alpha positions, hydrogen A and hydrogen B, of course, hydrogen A will be the ones that will be taken away because we have a larger base to obstruct the proton with. So let's go ahead and run over the mechanism. Okay. Lithium diisopropylamine, amide, form a double bond of electron density on the oxygen. We're going to form an amine. And at this point, I am going to flip the molecule. So my nucleophilic portion of the molecule is facing towards the right. So it's easier to put the mechanism together. Okay. I changed the wedge to dash because the molecule was horizontally flipped over, so it's the same molecule. And now let's react it with our electrophile. Electron density comes back. Let's attack this carbon. Pay attention, we have 2 double bonds. Let's see what will be left in the product. We're going to resonate electron density all the way to the oxygen. Let's form a new bond. And let's build the rest of the molecule. Okay, so this is our beta position. This is our alpha position. Just to keep track of those, electron density is going to move back. And as it does, we're going to end up placing the electrons on the gamma carbon. What did I do? Did I skip a carbon? No, I did not. And the last step is going to be obstructing the proton, and our base just got the proton, so we can easily give it back. And form the product. And here we are. So in this case, we see that we started with 2 double bonds in the enol, and we ended up with just 1 double bond in the product. You can see that that remaining double bond is still conjugated with your carbonyl double bond. So again, that is a good way to recognize your Michael addition product by the features in the molecule, okay? Any questions? So if there are no questions, let's run one more reaction with a different nucleophile other than enolate, so you will have the full variety. Another example with different nucleophile. Let's take a look at outcomes of this reaction. We definitely have an enone and a Grignard reagent as a nucleophile. The reaction will be done in diethyl ether. Let's take a look at the outcomes. Your Grignard reagent is going to attack this carbon. Now we have a cyclic compound with a metal group sticking up of the plane of the molecule. So the attack will be happening from the bottom. The electron density will move all the way to the carbonyl. Just like in the previous examples, electron density is going to go back, resonate all the way to the gamma carbon. And we will form the negative charge here. Now I want to spice up this problem just a little bit. Let's assume that we will put a substituent on this carbon. Let's put another metal group over here. So there is a metal group over here. When the electron density is coming back, understand that it will be coming back on the cyclic structure in which on the closest proximity to this carbon, let me put the metal group back in over here. On the close proximity to this carbon that is going to get the electron density back, we have an phenyl group that is pointing down. So the electron density will be most comfortably coming from the top. And as it does, it's going to push your metal group down. So let's just erase this and put a proper dash over here. Negative charge on carbon, okay? And of course, your second step, this is step number 1. Step number 2 for Grignard reaction is always to follow up with acidic wash. And we're going to obstruct the proton, move electrons back onto oxygen, and form the final product. That would be the major product of the reaction. I'm going to move on. And now let's see if we can predict the product of the reaction by given starting materials, and then go back to the product with the reaction conditions and see if we can recognize one of the starting materials.
Would we ever have to worry about maybe a linear molecule with a carbonyl end, like a double bond on both sides? If there's two conjugations.
If you have two carbonyls within the...
No, one carbonyl with a double bond on either side, that could resonate.
Oh, that's a very good question. So why don't we make an example like that, right? So you will have to worry then, since very, very good question, Sheldon. Since you have only one nucleophile, then you will be attacking from the side that is more electrophilic. I'm just going to make an example in honor of your beautiful question. Okay, so let's see. Another example here. So, and let's just use a different type of nucleophile here. What should we take as a nucleophile? Well, you know what? We're going to take just we'll just take a sulfide, okay? And we will react it with a nucleophile, with electrophile like this. There you go, okay? So definitely in this case, with just one equivalent of nucleophile, I'm going to choose the electrophilic position that is poor in electron density. So it's going to be this position versus position B, okay? And again, let's see if we can predict the product of this reaction without running the mechanism. My nucleophile is the sulfide, so I'm going to have, after the reaction is completed, indeed the first, so we're going to have a thiol on one side. Let's extend the bond towards our electrophilic position. Here is your nucleophilic position, and let's move on. So this carbon is the carbon that has reacted, so I'm going to go off of that. The right-hand side of the molecule off of the carbonyl did not change. I did have a nitro group on, and in this case, linear molecule, the nitro group could end up, that carbon could end up being attacked from top or bottom. So with that nitro group over there, being only chiral center, we'll end up with racemic mixture of two products. Linear molecule, if somewhere in the molecule you had unreactive chiral center, you would get a 1-to-1 mixture of diastereomers. Did this answer your question, Sheldon?
Would it not happen again, the react on the other side, if there was more nucleophile?
If you had more nucleophile, indeed it will. But if you have nothing to attack, then it's not going to happen. Okay?
Okay, thank you.
You're very
Mrs. O, I have a question. Why would you react it on position A instead of position B? I know there's an inductive effect, but even if you resonate towards the nitro group, that carbon, oh, you're resonating that way. Oh, okay.
Okay. Your
Okay.
nitro group is going to pull electron density from that carbon. Your carbonyl is pulling electron density from that position. So it's the poorest in electron density there. Okay. Okay, guys.
Sorry, one quick question. If we had an electron donating group instead, would that affect the reaction?
Very good question again. So this is Ellen's question. What if we had something like that on this side? Then definitely so. Your side A would be a better side because the electron donating group will actually make that carbon over here much less electrophilic because the electron density will never have a formal positive charge.
Thank you.
You're welcome. All good questions just before we are done with organic chemistry. So now let's make up a couple of other examples here. Let's see, on the go. Let's see what we can come up with. Let's see if we can predict the product of this reaction. In this case, we do have two alpha positions over here. With the small base, of course, I could remove the proton from more acidic position, position A, over here. But since I have an intramolecular reaction, will it be easy for me to attack the carbon on the electrophilic position from here? Let's see if it's possible. If I count the atoms between here, 1, 2, 3, 4, 5, I'm making a 5-membered ring this way. Now, if I attack with this carbon, the rings that I'm going to form will be 1, 2, 3, 4, 5, 6, 7. Here I'm forming 7-membered ring. By picking the electron from this position, I'm forming a 1, 2, 3, 4, and 5-membered ring. Indeed, we will be picking the electrons from this position. So when I form the product, and so you guys can see it clearly, I'm going to number 1, 2, 3, 4, and 5. So we can easily place the substituents. On position number 3, I have my carbonyl from the enone. And then I had only one double bond, so the double bond is going to disappear. Just so you guys can have good visuals of your reaction outcomes, I'm going to color label the carbons again, so you can see it very well. Your beta carbon, your alpha carbon, and the gamma carbon over here, that's your carbon number 4, does not carry an sp2 hybridized carbon anymore. Okay. So now let's see if we can predict the starting materials of the reaction given the product. Just a second. That should be good enough. So let's take a look at this example. Okay, here, what I see in the product is that I have two carbonyls. My carbonyls are pretty far away from each other. And as you can see, I didn't provide you with any of the starting materials. My carbonyls are far away from each other. So I'm going to decide which one of them is going to be my enolate and which one is my enon, based on the structural features of the alpha carbons around those positions, around the carbonyls. If I start with this portion of the molecule as my nucleophile, and I pick up this alpha carbon because it's leading us towards the other carbonyl. If this is my alpha carbon, then I should be able to see alpha position, then next to it, a beta position. And my beta position will be the one that does carry a double bond. Actually, no, this will not be possible. Give me just a second. Let me erase this. Impossible in this case. Okay, that is better. Kind of symmetrical molecule, but that's fine. So alpha position. Right next to it should be beta positions that in all of our examples did carry sp2 hybridized carbon. Okay, so I'm forgetting to put things on. Okay, here we are. So beta position, gamma position. From gamma position, the double bond is gone, and I still have a conjugated enon on the other side. So to recover my starting material, I am going to cut the bond between these two carbons, put my nucleophile in with the alpha position, and then place the electrophile. And erase the extra carbon here. This will be the beta position. We had two double bonds. We're left with just one double bond conjugated with the carbonyl. Another really maybe a good tip for you guys to recognize the Michael addition product is that the distance between two carbonyl carbons, if you had enolate and the enon to react, is this distance is always going to be an odd number of carbons. Okay. So that is your Michael addition reaction. The extension of this reaction is the Stork reaction. So let's take a look at that reaction. Really beautiful reaction, one of my favorites in this chapter. It is an extension of Michael addition reaction.